Yeah, he's putting it on Thursday instead of Friday this week.
Okay, so last time we talked about different UML diagram relationships. So when you have class diagrams, you can have different relationships between them. So I just want to quickly go over them at a high level again, just to make sure that we are all aware of them. So we had association, and association was just the most general and broad class of this relationship. It's for now that we've seen the other relationship types, talking about association and doubling back to it probably makes a bit more sense. So if there's no inheritance hierarchy associated with this, if there's no realization, so there's no instructions, kind of a setup and the printer setup plus printer class kind of relationship. If there's no association between a class and itself, then if you have two classes and they're still related in some way that's not one of those ways, you can just leave it as an association. We had a directed association, which added some directionality to the association. This says, yes, these are related in some way, but there's kind of a from to relationship in this diagram. We saw reflexive association. This one is one of the more complicated ones. So there is one or more airline staff related to zero or more, related to zero or more airline staff. And since this could be part of a hierarchy, maybe you could imagine a reflexive association in the middle of an inheritance hierarchy. This would allow us to say something like, there are subclasses of airline staff called pilot, aviation engineer, ticket dispatcher, et cetera. And rather than saying that all aviation engineers oversee maintenance crew members, the better way to state that there may be some relations in here is to say that some airline staff may be related to some other airline staff. And that's if the exact relationship wasn't apparent from just the classes themselves, in which case you'd want to draw the arrows between the subclasses that are related to each other. If all aviation engineers oversaw all maintenance crew members, then you could have some kind of association between them, or even a directed association between them. But if that's not the case for all of them, you can leave it as a reflexive association. Next, we have multiplicity. We talked about how an airplane can have zero or more passengers, and this helps us to be able to understand the multiplicity of the relationship. So something like a classroom can have zero or more students, although a class with 0 students would be really sad. Just imagine me sitting in here lecturing to an empty classroom. That's just kind of a sad thought. The really important one, the most commonly confused one, aggregation and composition. We talked about this being ownership is the easiest way to determine this. So aggregation is where no ownership is implied. Composition is where ownership is implied. So we had a car owns its wheels, but a project doesn't necessarily own its consultants. Similarly, we had students in this class. The class does not own the student, and the student doesn't own the class. CAT, on the other hand, owns its classrooms. We talked about the code example. This was a really important example. This is worth going back to ahead of the next exam, just to make sure that you understand the code and what the code looks like when we're talking about composition and aggregation. On one hand, the car owns its engine, and on the other hand, this instantiation of it does not own its engine. So, and then seeing how that perforates to the rest of the design of the class. If the engine is tied directly to the car, then there needs to be no check to determine if the engine is null, because every car has an engine. We know this because in order to construct a car, we need to construct an engine. The engine construction happens within the car's constructor, so that means that every car has an engine. In the aggregation example, that's not the case, so we need to check whether or not the engine is null. Does this car have an engine? If so, if it doesn't, then we can't drive it. It's not gonna do anything. If we try to call engine.work, we're gonna get a null pointer exception. Generalization was this concept of inheritance between classes. So we can have small inheritance hierarchies, we can have large inheritance hierarchies, but whenever you see an open triangle like this, it means inheritance. Sorry, an open triangle with full lines, because an open triangle with dotted lines is realization. So this is implementation of functionality defined in some other class. The example we used was printer setup and printer. So with all of these done, this is where we ended last time. We want to be able to see how some of these can be used. Here's an example, high-level project class diagram. So in this diagram, we have some projects, some activities, some tasks, and some resources. What was that filled diamond?
Ownership. Yeah.
It was either aggregation or composition. So yeah, you called it ownership, which infers that it's composition, right? So this would be composition. A project is made up of one or more activities, composed. That activity is owned by the project, right? That activity could exist in some other project, but if you're instantiating an activity, it is part of a project. The same thing for a task. An activity can be broken down into multiple tasks, but the tasks are owned by their activities. So we can start to read these diagrams, start to understand the actual relationships between these objects. And they tell us, as computer scientists, a little bit about the implementation. If there's ownership implied, then that is happening within the constructor to make sure that they exist. They're being tied specifically to the object in ways that you cannot uncouple them. They're tied together. When you make a project, there are activities. When you make an activity, there are tasks that represent that object, and you can't break apart a task and assign it to a different project because it's embedded within the activity object, which is embedded within the project object in ways that are tightly coupled. Then tasks are assigned to resources because we need to be able to run those tasks on particular machines, servers, something of the sort. And so it doesn't matter what project the task is associated with, you could assign to the same server tasks in lots of different activities or projects. So it's unrelated to that, but it's related to the same task. You can ask the question, what activity is this task a part of? And which resource is this task assigned to? And you get all of this from a very simple diagram. So you can look at this at a high level and start to understand a lot about how this design is produced. And it would give you an idea about how to implement it, assuming you knew what these relationships meant. So this is what a high-level project class diagram looks like. Does this tell us at all anything about how projects are actually, like what the fields and methods of the project is, the fields and methods of an activity, the fields and methods of a task? Maybe very little about the fact that there is composition. So we know something about how it's going to be designed and composed at a design level, but we don't actually know what they're called, what their return types are. So you can also have a detailed project class diagram that actually breaks them apart into their class diagram objects. So we talked about class diagrams that tell us things like, all right, we have fields at the top and we have methods at the bottom. We're going to group all fields together. We're going to group all methods together. And this tells us all of the variables, the fields. It tells us all of the methods and what those methods either take or return. How do we tell where the parameters are to these methods and where do we tell what they return? How can we see that from this diagram? Yeah,
All the methods have the colon and the return type after, and all the variables are in the top field.
yeah. So we can see in these methods that a getter, does a getter take a parameter? No, it only returns something. So we can get an idea, even without my describing exactly what this does. All right, what comes after this colon, outside of the parentheses, is the return type. The parameters, on the other hand, are between these the parentheses, because setters always take parameters and return nothing. So you can take the logic of how getters and setters work to be able to better understand this diagram without in-depth explanation. We see that the fields all have types, and this is just one such way of communicating this information. Like we said, UML is a union of modeling languages, so different modeling languages and different people will write this in a different way. So you may see a diagram like this, and it may not quite adhere to this exact same structure, but with knowledge like, what does a getter take? What does a getter return? What does a setter take? What does a setter return? Some of those are nothing. You can start to read these and understand them at a high level if you understand some of the components. You can still see that there are the relationships from the same high-level diagram. So this is the same diagram as this, except it's telling you what a project consists of, what an activity consists of, what a task consists of, and it has the same relationships between them, showing that we still have composition between task and activity. We still have composition between activity and project. It also tells you the associated number. Work effort is now going to be an inheritance hierarchy, because this is our generalization, right? This is a solid line with an open triangle, which means that we have generalization. So this is an inheritance hierarchy. Activities and tasks are subclasses of work effort. Questions about any of these diagrams or how to read them? Yeah.
So I see a open triangle go into work effort, and then task also has a filled triangle go into the activity. It can have multiple.
Yes, there can be multiple relationships with multiple different classes. So this is saying a task is composed, or sorry, an activity is composed of multiple tasks. And that's composition. As part of the activities constructor, it's going to make a list of tasks, probably some kind of collection of tasks. So it could be an array list, it could be a linked list, some collection. It could be a hash map, it could be a tree map, it could be any collection structure where we have the associated tasks. But both of those inherit from work effort, which means that some of what an activity defines, some of what a task defines is the same. And that can be kind of factored out into this work effort class that both of them inherit from. So there's not necessarily a single relationship between, there's going to be probably a single relationship between each pair of classes, but each class can have different relationships with other classes in your project. Excellent question. Anything else? All right. We're going to start going into lots of other UML types of diagrams. This is almost everything you need to be able to read most of the diagrams that are on Refactoring Guru, which is the most important thing for understanding the code smells that we've talked about, and especially when we start talking about design patterns. I will be referring to the site a lot in class. It is the first place you should go if you have any questions outside of class or want a better understanding of any of the design patterns that we cover. There is also the textbook that I have linked in Canvas, so you can access the textbook to read more about it as well. But especially Refactoring Guru is going to be giving you examples, and the examples that they give you are going to be in this form. I will also be going over some examples in class, but to be able to understand some of the examples that I don't go over, or some additional examples, you'll need to be able to read these kinds of diagrams. So very important that there's a base level of understanding here. I can always help with that, I don't think I've seen anybody in office hours, or I've seen a couple people for mostly unrelated reasons in office hours, but my office hours are absolutely there for helping you understand something. I'm here for you every step of the way in this class. If there's anything that I can help with, please don't hesitate to come find me and ask the questions. Students always think their questions are stupid. I don't buy it. Every question reveals something that can be learned. So the next one is an object diagram. And this is what happens when we instantiate a class diagram. So a class diagram represents that blueprint, right? When we write a class, we're not defining a particular object, we're defining an abstraction of that object. We're defining what that object consists of. If I were to define a person object, we would all adhere to that person object, but we are all separately instantiations of that blueprint of what a person contains and the behavior that a person exhibits. So unfortunately, object diagrams are becoming a little bit obsolete, but it gives you an idea of what a system looks like at a particular point in time. So here's an example of what that might look like. So we have a particular human resource system development, part of a project. So this tells you the instantiation. So each field has a particular value. Whereas before, each field just told you the variable type that it was. All right, we have an integer, we have a string, we have a date object, and we have an integer. And that is what a work at the state of a work effort consists of. Now we actually have values for those variables because they're instantiations of those objects. We're going from the abstract, talking about what does a person contain. When we're talking about a particular person like me, I have a particular name. It's not just a string. Every person's name could be represented with a string. But when we're talking about me instead of a generic person, that string has a value. So in this case, we can say name equals human resource system development. Description equals this is our project. The start date was a very long time ago, possibly before some of you were born, probably before most of you were born. Very similarly, this is kind of a snapshot in time. You can imagine that 5 seconds from the time this snapshot was taken, some of these values might be different. But it gives you a very right now view of your project. Here's an invalid object diagram. The reason is the activity should not be there. Not super important. This is mostly obsolete these days, but it is very important to be able to do something like explain or show what a system looks like at a particular point in time. A sequence diagram is going to show, all right, what happens when certain methods are called in ways that make certain tasks happen. What I mean by that is, all right, let's say, let's give you an example first. Here's a sequence diagram. This would show what happens when a member of a bank wants to query and say, what is my current account balance? We have the classes here. We have the bank, the account ledger, and the actual checking account. That is the type of object that they're querying, saying, what is the value of my checking account right now? So here is the sequence of method calls. The person calls get balance. Maybe this is just a button tap somewhere on their app. Maybe this is what gets called when they log in and you immediately see what your checking account's balance is. What's happening underneath the hood is you log in. As part of that login process, get balance gets called, which queries to the bank object. The bank object says, okay, now I can request the account with the account number from the account ledger. This returns the account number. So we now know which account, sorry, the actual account object. So we have the number here, this gets the actual account object, or a snapshot of the account object. With the snapshot of the account object, we now need to parse that object to figure out what is the balance within it. So we call get balance. But the account ledger doesn't have access to the balance. The checking account object has access to the balance. So we can call get balance from this checking account, which returns with the actual balance, returning it to the object that called it, which can then return it to the user and display it in some predisposed way. So the logic behind this process is significantly more complicated than you might assume that it is. And a lot of this reason is we need some separation between, like, it's pretty hidden, or it should be pretty hidden, what everybody's checking account balance is. If I log in and there's some way for me to access the account ledger, for instance, that's not where I shouldn't be able to access your balance or somebody else's balance. Or if we have separation of concerns here, we have objects that store these particular things, then the different objects have different abilities to interact with the different objects, which allow things like the only way we can get the balance is on login from this request. There's no other way to do it. If we do it that way, then it's going to be safe. But the important part of this is really just seeing that we can see time on this axis. We see the exact sequence of calls and the objects involved with those calls when the user needs to figure out the balance of their checking account. Here's exactly how this sequence of method calls happens and the returns happen that populate that. So now we can talk about exactly what it is. So you can imagine, we talked last time about what a use case is. That's when someone who's attached to the project has something that they want to be able to do. As a bank user, I want to be able to check my account balance so that I know how much money I have. So we talked about that as a I want to so that language. That would be an exact example of a use case of someone who is a member of the bank wanting to figure out how much money they have. That describes the technical process of the methods that are called and the objects that are involved in being able to answer that question. So things you need to think about if you're designing a sequence diagram: what are the associated class roles? What is each class doing? The lifelines: how long does this object exist? Because you're going to be creating objects and destroying objects throughout the life cycle of your program, right? So you need to know, when does a class become a thing? When does that class go away? We need activations. How long does it take for an object to perform an operation? Does anything need to be happening in the middle of that? As well as messages. What are the communications between objects? What are the parameters in the methods that are being passed? That's information sharing, or the return value from a particular method being called, that is information retrieval. Another example for this is what it looks like to possibly check your email. So from an end user's computer, the computer is going to receive the check email command. This makes much more sense if we're not using an online email, if it's something like Outlook on your computer, not Outlook on the browser. So you have some email app that you're using, and you click something like refresh your inbox, or maybe there's a generic button for check your email. So the computer then to the server needs to send any unsent email. It's a very old version of how email used to work. Request new email, get a response from the server that says, yes, I can handle this right now. And then with that new email request, download all email that is new since the last time you checked. And then you can also pass along, delete any old email that is more than some number of days old. Something like this, but it describes how that process works. So this is the communication between the computer and the server. We can see information that's being sent from the computer to the server. We can see any response from the server back to the computer that says things are good, which might tell us the kinds of errors we need to display if, for instance, we don't get a response from the server, or if the response from the server can't be parsed in a way that we expect it to be. The response from the server should be in a particular form. If it's not in the form that we're expecting, there's an error that can be stored on the computer that we throw if the server doesn't give us what we expect. Here's another example. We have a project manager. We have a user interface. We have the objects for projects and activities and tasks. So the project manager decides that, all right, we've finished this particular project, so we want to remove it. So the user interface needs to go fetch the associated project. So it's going to take in the name of the project, and it's going to go find the project and return the project. Within that project, we need to find all activities within that project. Within each of those activities, we need to find all of the tasks associated with that activity. As we find all of those tasks, we're going to remove the tasks from the activity until there are no more tasks in that activity. And of course, we're doing that for each activity for the entire project. Once all tasks are removed from the activity, we can safely remove the activity. Once all activities are removed from the project, we can remove the project. We can see that there's a nice logical sequence of events here that allow us to go from the start to the end. It defines what that process looks like. Question?
Is that true for all sequence diagrams?
Yeah, it's defining a particular sequence of events. Of what happens internally such that that event can happen. And you might draw this for any potential important sequence, but you can imagine as a programmer, if you had access to something like this, you could come up with an algorithm that accomplishes exactly this sequence. It defines all legal ways to solve the problem. So it's good communication, and it's also something that is very accessible to a client. A client who's reading this says, oh yeah, that makes perfect sense. That's exactly how I want the project to be removed. So it's very accessible to all members of the development team and all clients, other people who are involved, sponsors who are funding this activity, funding this development. Everyone can read this and see this and say, yes, this makes sense. So this becomes part of your project's documentation. You can imagine now that when we instantiate this process, here's an example of what this process would look like. We want to remove the project human resource system development. We find all of the associated activities. We find all of the associated tasks of those activities, and then we remove them in that kind of recursive order, where we now say, all right, once all tasks are done or removed, we can remove the activity, check the next activity, and this looks very much like a depth-first search or a recursive removal of all of these tasks. This is exactly what happens in a computer if you decide to delete a folder, for instance. If you delete the folder, but not the files inside of the folder, you're using the same amount of hard disk space. You're not actually freeing any hard disk space, right? Folders don't have any size, really. They're just location pointers that say, where are these files stored? They're stored over there. If you delete what is pointing at the files, you're not actually deleting the files. And in fact, you don't have access to the files anymore because you don't have a way to say, all right, follow this pointer to where the files are. So you want, before you delete the folder, you want to make sure that you go delete all the files and then delete the folder that tells you where the files are. When there are 0 files, removing that pointer makes sense. All right, next we're going to talk about activity diagrams. If you've seen flowcharts before, it'll use flowchart symbols, and the emphasis is on exactly how the process works from start to finish. So here's an example of receiving an order for some kind of maybe online store. So whenever you see a bar like this with multiple arrows out of it, it's a fork, which says that these activities are happening at the same time, and different people are responsible for each of them. So when you receive an order, different people are responsible for filling the order and sending the invoice. They can happen in parallel. You don't have to wait to fill the order to send the invoice. You don't have to wait to send the invoice to fill the order, they can happen at the same time. So from this fork, we're going to fill the order and send the invoice, but after the order is filled, then we have a branch says that either we're going to have an overnight delivery or a regular delivery, depending on circumstances. So we either rush the order or we don't, depending on whether we have an overnight delivery or a regular delivery. Whatever happens with that, we're gonna merge back together, because regardless of which delivery was done, we need to be able to close the order. But we cannot close the order until we receive payment. So these merge back together after the fork to be able to close the order, but only after the delivery has been finalized. Basically, we know whether or not we're doing an overnight delivery or a regular delivery, and we have received payment. After that's the case, then we can send off the item and close the order and terminate, reach a final state. That's what this end represents, is that we've reached the conclusion of this sequence that defines how this is done. And once again, there's no class defining anything of what the fields and methods are. This is just kind of a way of showing from start to finish what sequence of events need to happen. So this is the same diagram with most of the words removed, as well as the associated departments that would be responsible for each of these things. So you can now start to understand, what is the fulfillment center? What are they waiting on? They're waiting on receiving an order. As soon as an order has been received, the fulfillment center can start fulfilling the order. Customer service is going to be responsible from the very beginning of receiving the order. But now it kind of tells you that in order for the fulfillment center to start fulfilling or filling the order, they need to receive something from customer service with the order. So it now tells you department by department who's responsible for what are the communication lines between those departments, and what are they responsible for. So all of this can be seen within a single diagram in a way that shows exactly how this is done. Exactly how this is going to work. Questions about either the last couple slides about what these diagrams do, how to make sense of them? You can also kind of draw boxes and make sub-diagrams for each of these. So the delivery sub-process of the entire order, you can see, has a separate starting position and a separate ending position. So this represents kind of the final state, saying everything has been done. This is the final state for the delivery. Here's where the delivery begins, here's where the delivery ends, here's exactly what happens within the delivery sub-process. You could even mark this as a single delivery thing and have a separate diagram on a completely separate page that goes into the details of what delivery looks like, where you specify this diagram. There's nothing that says that it all needs to be encapsulated in a single diagram. So the design of a good UML is very much like the design of code. There's no one right way to do it. You just want to make sure that it's clear to whatever extent is possible. All right, let's try a little example here. All right, we have the following situation. We're going to accept payment and send an order to the warehouse to be delivered in parallel. The warehouse throws an exception to denote that the product is not available. So we now need to put the charge back on the end user's credit card. How do we handle exceptions to this? Here's an example of an interruptible flow diagram. So we start, we process the order. At any time between the processing of the order and the closing of the order, the user can have a request to cancel. If the order is canceled, then we reach that same final state that says we're done processing the order, except we're not going to ship the item. We're not going to close, we still probably, possibly, we're not closing the order, we're canceling it. So it's interruptible until the order is closed. Once the order is closed, then they have to go through a refund because the order has been shipped. But before the item has been shipped, they can cancel and get a full refund. So that's how this is embedded within that process, the activity, sorry, the diagram here. Questions on any of this communication, how diagrams can show any of this information? Yeah.
Just a quick question about that scribbly arrow.
Yeah.
Why is it scribbly?
So it kind of shows, it's a visual way to show that this is an exception. Yeah, it's exceptional behavior. We don't expect the user to cancel the request, but if they do, here's how we're gonna handle it. Great question. So I think we're starting to see just how important communication is for computer scientists. I know that stereotypically, computer scientists are not the most communicative people, but it turns out to be one of the single most important skills you can develop, because you're going to need to be working with other people. You're going to need to be working under people, under higher ups. You need to be able to communicate with your coworkers, communicate with your higher ups, communicate with your clients. All of that is going to use different kinds of language. So communication is super important. You need to avoid pissing off your coworkers. You need to figure out how to work together. You need to figure out how to talk about how you're doing with your code and the issues that you're running into in ways that they're going to understand, that they can possibly help you with. Writing, speaking, communication, all vital skills for software development. So it's something that if you feel like that might be a weakness of your person right now, think of it as something that you can work on over the next couple of years. Try to break out of your shell, try to figure out how can I proactively communicate when there's something going wrong. The way that I think that you can work on that between now and then is, as soon as an issue crops up in a class, talk to your professor, advocate for yourself. As that happens, you will learn how to initiate that conversation for something that's important to you that someone else might not recognize. That skill translates to the workplace and will be vital for your success in the field. And it's just useful all around anyway. You'll get the most out of college if you can consistently advocate for yourself. Next diagram is an activity diagram. So we have some lanes, some action lanes, action flows, object flows. So swim lanes are the responsibility of one or more objects. Action states is how the algorithm executes what goes on step by step. Action flows, relationships between the different action states, and object flow, the utilization of objects by those action states. So again, this is very similar to this. We have the lanes that we start to see, the fulfillment lane, the customer service lane, the finance lane. So that's more of an activity diagram type. And again, it looks very similar to, we just talked about not calling it an activity diagram, but it showed up in a, I guess this was still an activity diagram, but yeah, you can see that you can continue to produce more and more information from this by thinking about and showing these associated lanes. State chart diagrams. These are something like hierarchical finite automata. If you want to know what a finite automata is, take compilers from me. I can go into that in so much more detail. But the basis of a finite automata is it's just a state machine, which means that we have some kind of, for those taking data structures, we know what a graph is. A computer science graph, not like a graph from a math class. So there are vertices and there are edges connecting those vertices. So we have states and we have ways that we can transition between those states in ways that tell us something about how the current state of our application. So an example of this might be a button that is either pushed or not pushed. When you press down on the button, you push the button goes from off to on. And when you release, the button goes from on to off. This is a very simple version of a graph where we have two vertices that represent the state of the button being off or the state of the button being on. And And then we have transitions. The off to on transition involves the action push. The on to off transition involves the release of that push. We call it a finite state machine because there are a finite number of vertices and edges in the graph. Here's another example of what a state machine might look like. Here is a resource diagram. A resource is either not assigned or assigned. If it's not assigned, we can assign it and increment the number of assigned tasks as we do so. That means that that task is now assigned to a resource. And if it's assigned, then we can loop around and stay assigned until we get the unassigned behavior or request. When we get the unassigned request, then we transition back from assigned to not assigned. And in the meantime, the resource is idle and the resource manager gets notified that, hey, this particular resource is not being utilized. You can send it some more tasks now. And this just defines what that process looks like. A resource either has no assignments or assignments, and like that. Questions on the concepts of graphs or how they apply to these finite state machines that can help us to be able to describe the state of some process? Another example, this one's much more complicated. There are now more than two states or more than two vertices. A beer glass state machine, you start your beer glass being clean and empty. If the customer orders beer, then it gets filled and it contains liquid and the cup is now in service. You can't go collect that glass while it is full. Have you ever had a waiter come and just take your very full drink? That seems wrong, right? Like something that shouldn't be allowed. That's now built into this state machine. It contains liquid and it's in service. So a transition from this happens when the customer drinks the beverage. Once it does so, it's empty. You don't want to go fill an empty glass that's the customer already has while it's there. You can't do that. But if the customer reorders and says, yes, I'd like another drink, then we can pour another, go back to containing liquid and being in service. So we can define this loop. And this allows the customer to order any number of beverages. So we just have this loop in this state machine that says that there's no real limit to the number of orders. Maybe this makes more sense for a drink that's not beer, because there should probably be a limit. Can't order 25 of them, the poor person's gonna end up dead. Once the customer declines a drink, then the glass is now dirty and needs to be washed before it can be used when another customer orders another beverage. You don't wanna take someone else's dirty cup, fill it up with a beverage and hand it to someone new. That's a very quick way to not have a business anymore. But this exists, this shows you the state machine for the relevant states and transitions associated with this activity. It doesn't even necessarily have to be a virtual activity or a computer-related activity. Any activity can be modeled with this kind of state machine. All right, last couple things. We've now covered basically all of these kinds of diagrams. We talked about use case diagrams, class diagrams, object diagrams, sequence diagrams, activity diagrams, and state diagrams. Of these, the most important are the class diagrams. That's what's going to be mostly used for this class. But for UML in general, you're going to start seeing more and more of these diagrams, or maybe asked to write some of these kinds of diagrams. So just knowing in general what they represent can help you to be able to tie the material that you need to represent with some way to represent it visually in a way that leads to easy communication between all associated parties. What's good about UML? Well, it's a common language. It's kind of like math. Most people can understand these diagrams. So this helps you to be able to do things like, what does this application need to be able to do? That's what when we talk about requirements, what are the constraints on the system? What does it need to be able to do? Specifications, designs. Once we figure out what it needs to be able to do, we can come up with what are the components? How do those components interact and communicate with each other? How does that meet the requirements of the application? So a good picture is worth a ton of words, right? If you were asked to write something to describe even the last example, you would need a lot of words to be able to describe this entire process, everything that is possible. You would imagine you probably need something like a page worth of a text requirements document to be able to describe this process. So figuring out ways to draw, it doesn't have to be perfect. I have terrible visual productions myself. I don't draw the best pictures that represent complex things. I don't have great artistic skills, but if you can logically represent something in a good picture, then for those who aren't necessarily programmers, then it will be much better than writing out the associated pseudocode. And it can almost give you as much information as pseudocode. So to the extent to which we can be precise with these diagrams, we are clear with them, which means that there's very little room for misinterpretation because the requirements are right there. It's also much better than natural language because English is ambiguous. I can say the same statement and two different people can hear that in two different ways and understand different things about it. If we have these diagrams, there's clarity to those diagrams in ways that can't be misinterpreted the way that natural language can. It's good for support. What's bad about UML? You probably see this every single slide as a new idea or completely different subset of how to represent some of the same things differently or some very different things in different ways. So it's kind of just a hodgepodge of ideas. And then this visual syntax does not scale particularly well. You can't represent a 100 state finite state machine easily in one image. So imagine instead of 4 nodes here, 4 vertices, we had 100 of them. What would that image look like? It's gross. We cannot easily visually represent complex ideas. So the way that we're getting around this is that we have text attached to diagrams, and we saw that throughout a lot of the diagrams that we covered. There was just text attached to them, and that's not really pretty or easy to read, or it can lead to some misinterpretation about what is the text actually attached to. It could also introduce some ambiguity in that language. You attach the text to it and people are going to read it or see it differently. So if instead of 1 picture, you need 1,000 pictures, it's very difficult to, all right, here's picture number 1, here's picture number 2, picture number 3, picture number 4. All right, how do these interrelate? What is it that I'm supposed to be visualizing with all of these different pieces of paper that show different things? It can be very confusing. So it's not a one-stop answer to the complexity of modern applications, but it's a starting point. It's widely adopted by just about everybody. It's a step forward from not having it, but I do not think that it is the final solution. If we come back to this problem in 30 years or 50 years, we're probably going to have something better or more well-refined than the current version of UML. So just because you've memorized this for now does not mean that it's going to be relevant forever. Keep your eyes and ears open for news about how this is changing and adapting to the world around us. Wow, I used exactly the amount of time for class. I thought we might finish early. We did not, but we got there, which is important. I have a decision to make about tomorrow. Either we're going to dive into design patterns starting tomorrow, or we may also have 2 days this week where we get some programming experience and problem solving experience. So we'll do one of those things tomorrow. Thank you. Thank you.
So is there like a certain repository that would hold all those information about UMLs and everything?
Just like in general, all of the information.
Yeah.
Yeah, there's, I don't know off the top of my head, but a quick Google search would probably reveal where the history of that adoption and all of the information about UML is stored. And that would just be someone trying to collect all of it because there's no real single answer to all of this.
Oh, yeah.
Everyone sees it differently, uses and has different appreciations for different aspects of UML. It's a tough world.
Have a great rest of your day, so.
You too, have a great rest of your day, see you tomorrow.
See you tomorrow.